Welcome back. Today's explainer is an absolute must-have if you're tackling IBDP computer science, specifically topic B2.2.4. We're zeroing in on the queue data structure. You know, if you've ever wondered how your computer juggles a million tasks without just dropping the ball, well, you're in the right place. We're going to break this down step by step so you can totally master the operations and, more importantly, crush it on the exam. So let's dive right in, shall we?
All right, here's our roadmap for today. We'll start with the FIFO rule, look at the 4 core operations, trace queues in action, check out performance and memory, and finally, figure out how to choose the right structure.
Okay, kicking things off with Section 1, the first in, first out rule, understanding the basics.
Now I want you to picture this for a second. You've been waiting at your favorite coffee shop for like 10 minutes. You're finally up next. And then suddenly, someone just waltzes right through the door, completely ignores the line, and orders their drink before you. Seriously infuriating, right? You'd probably shout, "Hey, there's a line here." Well, believe it or not, in computer science, a queue exists to prevent exactly that kind of digital line cutting. It's basically the ultimate enforcer of fairness.
And that leads us perfectly into our formal definition. A queue is a data collection that strictly, and I mean strictly, follows the FIFO rule. FIFO, first in, first out. So what does that actually mean for us? It means the very first item added to the structure is absolutely the first one to be removed. It's just like that coffee shop line. Items join at one end, which we call the rear, and they leave from the other end, the front. It's a rock-solid guarantee that a program will process items fairly in the exact order they showed up.
Moving right along to Section 2, 4 core queue operations, looking under the hood.
Here's the best part. To totally master queues, you only need to memorize exactly 4 operations. Just 4. That's your entire toolkit to control this whole data structure.
Let's unpack that toolkit. First up is enqueue. This is super simple. It just adds a new item to the rear of the queue. Literally, just a person joining the back of the line. Second, we have dequeue. This one removes and returns the item at the front. Think of it as the person at the front getting their latte and leaving. Now, I need you to pay close attention to the third one, front. The front command reads the item at the very front of the line, but, and this is key, it doesn't remove it. It's just taking a quick peek. Trust me, knowing the difference between taking a peek with front and actually removing an item with dequeue is an absolute game changer for exams. And finally, isEmpty. It's exactly what it sounds like. A quick check that returns true or false if the queue is empty.
All right, Section 3, tracing queues in action, step by step.
Okay, this is where theory becomes practice, and honestly, this is a massive point score on exams. Let's trace a queue together. Imagine we start with a totally empty queue. Step 1, we enqueue the number 8. So our queue is now just 8. Step 2, we enqueue 3. Remember, new arrivals go to the rear, so our queue is now 8, then 3. All right, step 3 we call front. Now remember, what we just said, this just peaks. The queue stays exactly the same, 8, then 3, but the output is 8, because 8 is at the front. In step 4, we finally dequeue. That earliest item, the 8, is officially removed and outputted. That leaves only the 3 in our queue. Step 5, we enqueue 5. The queue becomes 3, then 5. And wrap it up with step 6, another dequeue. The 3 has been waiting the longest, so it gets pulled out, leaving only the 5. You see what's happening here? No matter what gets piled on the back, that earliest arrival stubbornly sits at the front until it's specifically dequeued.
And this brilliantly translates to code. Now, sure, larger applications might use more complex setups, but a simple Python list is actually perfect for seeing this behavior in action. Look at steps 1 and 2. We're using the append method. That's our enqueue right there, adding A and then B to the rear. Step 3 prints index 0. That's our front operation, just peeking at the first item without touching it. And step 4, we use pop0. That is our dequeue, physically removing the item at index 0 and shifting everything else forward.
So if we were to run that little Python script, the expected output perfectly matches the logic we just traced. That first A you see comes from our front operation, just peeking at the line. The second A is from the dequeue operation, which finally serves A and gets it out of there. Oh, and if we ran an empty check right after that, it would definitely return false, because B is still just hanging out, waiting patiently in line.
Moving to Section 4, performance and memory usage. Efficiency under the hood.
Now, it's not enough to just know how a queue works. You really need to understand why we use it, efficiency-wise. And queues, they are incredibly fast. In a solid implementation, enqueue, dequeue, front, and empty are usually O of 1. Basically, they happen in constant time.
pretty much instantly, because you don't have to reorganize the whole data structure every time you do something. But, and there's always a but, right? Memory is the flip side of that coin. Every single stored item eats up memory. Since dynamic queues just keep growing as new items show up, a massive queue is going to cause your memory usage to spike. Huge exam tip for you here. Whenever a question asks you to evaluate a data structure, always mention speed and memory together. It shows you see the big picture.
All right, bringing it all home with Section 5, choosing the right structure. Queue versus stack.
Honestly, the best way to really lock in when to use a queue is to put it head-to-head with the stack. A queue is FIFO, first in, first out. It's all about fairness. Think ticket lines or documents sent to a busy office printer. The oldest request gets the priority. A stack, on the other hand, is LIFO, last in, first out. Think of the undo button when you're typing an essay. You don't want to undo the very first word you typed 3 hours ago, right? You want to undo the typo you literally just made. So stacks are for reversing recent actions, while queues are strictly for processing things in arrival order.
Because of that strict fairness rule, there are a few classic, real-world queue applications you should definitely memorize. Printer jobs, for sure. You don't want some massive photo file cutting in front of a quick one-page text doc. Customers waiting for any kind of digital service. Task scheduling in your operating system, where older tasks absolutely need to be processed before newer ones. Oh, and for you advanced algorithm folks out there, queues are literally the backbone of the breadth-first search.
Before we wrap this up, let's look at a few common traps so you can dodge them completely. First, do not mix up FIFO with LIFO. Just picture that coffee shop line. Second, and I see this all the time, don't make the mistake of thinking dequeue removes the newest value. It absolutely does not. It removes the oldest, earliest arrival. And lastly, never forget that front only peaks. Keep those straight and you'll save yourself from losing easy points. I want to leave you with an incredibly powerful sentence starter. Whether it's an exam or a technical interview, if you have to justify using a queue, start with this. A queue is suitable here because the earliest item must be processed first. Boom. It instantly proves you get the core mechanics of FIFO. So here's a thought for you to chew on today. Look at the apps you're using. When you send a text, download a file, or even just stream a video, is there a digital queue silently working behind the scenes right now, just keeping everything fair and orderly? Thanks for hanging out with me for this explainer. Keep exploring and I'll catch you next time.